Thanks for having me. So I'm going to talk about this topic, optimizing attention for modern hardware. This is at the intersection of machine learning and systems, and there's been tons of progress, especially recently. So I just want to tell you guys about some of the progress, and feel free to stop and ask questions. It's relatively informal. Um, okay, so just to motivate, the problem we're trying to solve is we want to model long sequences. Why we want to do that? So in NLP, we want to deal with large contexts to understand books and plays and code bases. In computer vision, we want to model high resolution images for better and more robust insight. And in a bunch of new areas like time series, audio, video, medical imaging, um, we've seen that net data is naturally modeled as sequences of millions of steps. So the challenge for modeling song is one of the challenges is that attention can take a significant fraction of the time, um, and how do we optimize attention from modern hardware? So as an example, FlashAttention was already quite optimized for A100. They can reach about 70% utilization. But on H100, if you just take that code and run on H100, you would get around 350 teraflops per second, whereas the theoretical max is around 1,000. So we're getting around 35 to 40% utilization. That means there's quite a bit of headroom, right? And so I'll talk about a few techniques based on the work that we've done on FlashAttention 3 with folks at Kofax, Meta, and NVIDIA. So how do we optimize for new hardware? Sort of the baseline is that we should be using these new instructions, and I'll talk about how these new instructions help speed up attention. But more importantly, on the algorithm side, we have to sort of rethink the algorithm. We have to overlap things quite a bit more. Things are very asynchronous, and I'll talk about that. And we want to use low precision, right? And so these are sort of baseline, sort of table stake techniques, and a bunch of more advanced techniques that I will touch on, things like persistent kernels, longest processing time, first scheduling, DQA packing, and optimizing for MOA, multi-head latent attention. The upshot is this can make it about 1.6 to 3x faster for Hopper, and all of these ideas actually apply to Blackwell as well. So that's in the work. So let's see. So the baseline is we should be using these new instructions on Hopper. One is called warp group MMA. MMA stands for matrix multiply accumulate. So that's the tensor core instruction. And this new instruction has quite a bit higher throughput than the older generation instruction, MMA sync. So if you take your A100 code, which uses the MMA sync instruction, and run on H100, you're not going to reach a peak throughput. You have to use the new instruction. And now I'll talk about why the new instructions are different. And you want to be using this the TMA, the Tensor Memory Accelerator, because it is a specialized hardware unit that takes care of loading memory and do all the index calculation. So this saves a bunch of registers. And more importantly, as I mentioned, it's a lot more asynchronous, right? So what you do is these are specialized hardware units, the new tensor cores and the TMA. So you issue some instruction, and the hardware would execute them. Meanwhile, you can do other work. And I'll talk about why it's important to do other work while these instructions execute. So why do we want to overlap and do asynchronous instructions? It's because usually for attention, there are two components. There is the gem, the matrix multiply, and the softmax. So matrix multiply refers to the Q times K. And then when you have the attention, you take the attention times V, right? The softmax is the central part of attention. So why do we want to overlap them? So if you work out the math, turns out the hardware unit responsible for doing exponential has very low throughput relative to tensor cores. Or put it another way, the tensor cores are so fast, has much higher throughput than the unit that computes exponential. So as an example, we don't have to work out all the numbers here, but let's say for a block of 128 by 128, head dimension 128, then the tensor core instruction, even though it performs millions of operations, takes about 2000 clock cycle. So clock cycle is around, think of it as 1 nanosecond. Right? Whereas the exponential unit, it performs 3 orders of magnitude fewer operations, but it also takes around 1,000 cycle, simply because the throughput of the exponential unit is 16 ops per cycle, whereas the throughput of the tensor core is like 4,000, right? So it's a huge factor difference, right? And so you can work this out, and you see that the exponential unit takes 50% the cycle of the workgroup MMA. So this is for FP16. If you go to FP8, the tensor core gets twice as fast, but the exponential does not. So that's even worse. And if you go from Hopper to Blackwell, again, the tensor core gets twice as fast, right? So it's clear the future is the tensor core is going to get bigger and bigger. They're going to be faster and faster. So that means that anything that's non-tensor core, we want to overlap. That means we want the tensor core to be busy doing matrix multiply while all the other units are computing whatever is needed, so that the tensor cores are always busy. Right. Okay. So how do we overlap? So one easy solution is you don't do anything. So by default, the hardware already has these warp schedulers that can do this automatically for you. This works reasonably well, but we can do better. So here's an example. It's called ping pong scheduling. So for each thread block, you would split them into 2 warp groups. Each warp group is around 128 threads. And the idea is you want one warp group to be doing gem while the other warp group doing softmax. And then they switch role. And then, so here's an example. Here's the timeline. And different colors correspond to different iterations of attention. So you could have work group 1 doing softmax while work group 2 is doing gem. And then when work group 2 is done, then work group 1 would do the gem one, which is probability times V, while work group 2 is doing softmax, and so on. And you could put explicit synchronization points here to force them to line up this way. And this helps quite a bit. You can increase throughput from 580 teraflops to 640 teraflops, right? So that's great. One more new feature of the hardware is that it supports lower position. Why do we want to do this? It can double the tensor core throughput. It would reduce half the size of the KV cache, but it has certain implications in terms of accuracy, right? And one technique to deal with the lower numerical error is called incoherent processing, and this has been around for a while. So what happens is we're trying to solve the problem of outliers in LLMs, which is that usually there are some very large values and a bunch of smaller values, right? So when you quantize sort of naively, you get very high quantization error. So the idea is you want to rotate things Q and V so that you can spread out the outliers. So mathematically speaking, attention is just measuring the how similar the queries and the keys are. So if you sort of rotate them by the same angle, and here we're going to rotate by an orthogonal matrix, then the attention course stays the same. But what happens when you rotate in the original coordinate, if they're outliers, you can have very large values. But as you rotate, in the new coordinates, the values are sort of weighted combination of the old values, so the outliers get spread out, and as a result, you can reduce the numerical error quite a bit. So here we're comparing numerical error of with incoherent processing is about 2 to 3x smaller numerical error compared to no incoherent processing. Okay, so I'll pause these. So these are sort of the basic techniques, and then to see if you guys have questions.
Yeah.
Yeah.
Do you store the KV cache already rotated, or do you always, when you load it, do you need to recompute the?
Right. So you should store the KV cache rotated already. So for the K, you should rotate already, and for the Q, every time you have a new Q, you're gonna you're gonna need to rotate again.
Thanks.
All right. Okay, so those are sort of the table stake basic techniques, um, and that's been widely applied. Now I'll move on to talk about some more advanced techniques. One is called persistent kernels, and the goal is to hide prologue and epilogue. So the motivation again is to tensor cores so fast, everything else is just um, much slower in comparison. And in particular, these prologue and epilogue. Um, and the idea is we're gonna, instead of launching as many thread blocks as there are pieces of parallel work, what we're gonna do is we're gonna have a fixed number of thread blocks of CTAs that's equal to the number of streaming multiprocessors on the GPU. And each CTA or each thread block is gonna work on multiple pieces of work. And the idea is we're going to use asynchronous TMA to overlap prologue, and the main loop. So let's see how that works. So in the work tile, you can think of it as one piece of parallel work. There's always some prologue, which is you first need to load the query, and first need to load the key and value block, right? And here the tensor cores are idle, it's just waiting for data. Then the main loop, which is when the tensor cores are busy computing, but we'll also prefetch the next KV. And then at the end, you write out the output in the log summary, right? And during the epilogue, the tensor cores are not busy. But what we can do is we can have another work tile. We can start loading the query and the KV for the next work tile, while the main loop of the first work tile is still ongoing. So this is because of asynchrony on the newer hardware. So things like TMA, you can issue instructions and wait for completion later. Right? And then we can then proceed with the main loop as soon as the main loop of the first work tile has finished. So we see that there's overlapping between the epilogue of the first work tile and the main loop of the second work tile. And then finally, we could still finish the epilogue of the second work tile. So with this style of persistent kernel, you can improve the speed from around 670 to 700. It's also useful in a bunch of other cases that I'll talk about. So that's one more advanced technique.
Is it
Um,
for
yeah,
pre-filling?
yeah. This is for pre-filling. Yeah,
So
I'll talk about decode in a little bit.
FlashAttention is only for pre-filling?
No, you can also use it for decode. I'll talk about some of the optimizations for decode later.
Thanks.
Yeah. Another technique for again focusing on pre-filling is you need to do better load balancing. So the challenge here is doing if you're doing causal attention, which nowadays is most of the cases, you're going to have unequal amount of work per time. So let's see how that works. So here's an example. You have two different batches. You have three workers. Each batch sort of has four work tile. One work tile is one unit of work. Here is just a horizontal band. And because it's causal, we're only going to compute sort of the blocks that are shaded. Blocks in white, we're not going to compute. Right. So if you schedule as usual, which is the first come, first serve, and that's what we've been doing for the last 3 months, so it's 3 years, is let's say you have three workers. So the worker one will show up, it will take care of this work tile, worker two will work on this one, and worker three will work on this one. And as you move through time, every time one worker finishes one work tile, it get assigned the next work tile, right? So this is sort of the first thing you would think of how to assign the work. And as you keep going, you see that towards the end, pretty much all of the workers have finished except for the last one, and still working on the last tile, right? And so in this particular example, it takes about you have this unequal distribution of nine blocks for the first worker, and then 5 and 6 for the other workers. And now that we think about it, it seems like yeah, this is because we schedule sort of top to bottom, so that the longest tile at the bottom is always scheduled last, right? And um, show this to my cat, and he's not so excited. Um, so how do we do better? So now that we understand the problem, which is the longest tile gets scheduled last, the idea is we can schedule the longest tile first, right? And it's not a revolutionary. Back in the 1969, people were already analyzing this kind of algorithm, right? So it's not a new idea. So let's see how that works. So now we're going to assign the work tile from longest first. So let's say two workers show up, 1 and 2, they get assigned these long work tiles. And then worker 3 show up and is going to be assigned this next work tile. And then each of them will work on their work tile until one of them finish. So if number 3 finish, it get assigned the next longest work tile. And we just keep going. And as before, so in this case, it only takes it takes 7 time steps to finish all the blocks, right? Because the shortest work tile gets scheduled last, and in this particular case, the work distribution is 7 7 6. Was previously it was 9 5 6, right? So it's quite a bit better balance. So I show this to my cat, and he's a lot happier. So the only caveat is that because we schedule on the long tiles first, you have to take care not to spill the KV cache. Sorry, it's not the KV cache, the L2 cache. Um, because otherwise, if you schedule on too many long tiles, they all need to be loaded to L2, and they could overflow the L2. So you just have to take into account that L2 has some limited size, so you can use this technique called L2 swizzling, and this makes the causal attention go from around 670 to 730 teraflops. So overall, let's see how that works. So with BF16, we get around sometimes more than 2x speed up. And I'm comparing to FlashAttention 2. cuDNN is actually also really good. cuDNN uses very, very similar techniques it's the work from the folks from NVIDIA. We've had a great time talking to them and learning from them, and they've been implementing some of our techniques as well. So cuDNN is also really, really good. I think some of the more advanced techniques like load balancing and so on sort of helps you increase the throughput. This is for prefill a little bit more, things like persistent kernel and load balancing. Um, and you can get, even for causal attention, you can get 73 to 730 to 750 teraflops per second, which is around matrix multiplication speed, which is actually crazy to think of, because this is actually quite a bit more complicated than matrix multiply, right? And matrix multiply is pretty much the most optimized operation on the planet. And so we've gotten pretty close to matrix multiplication speed. If yeah,
Isn't attention memory bound if you have a very, very long context window?
right. So it's memory bound during decode, but during prefill is actually still compute bound. Like we've gotten to the point where it is compute bound.
Hmm. Cool. Very cool.
Okay, and if you increase the head dimension to 256, which is less common, but actually more hardware friendly, you can get to around 840 teraflops, which is pretty crazy. And with FP8, you can get to around 1.3 petaflops on the 8100. Okay, so I've talked a bunch about sort of prefill also applies for training. So I'll talk about some optimizations for decode, right? And for decode, usually the query is much shorter. It could be 1 token or a couple tokens if you do speculative decoding, but the context can be quite long. And so the standard way of doing this, and this is the work we collaborated with the folks at Meta, is that you can split the KV cache into multiple splits. So you can have split into 5 splits and have individual different thread blocks computing attention with respect to each of those splits, right? And at the end, you do a reduction to compute the final output. This is so that you have more parallel work for the GPU to do. And this is now pretty much standard. Almost all of the um, libraries and packages would use this kind of split KV to compute attention during decode, right? But GQA has gotten quite popular. It's pretty much standard now. Things like Llama and Quen model uses GQA. Um, and with GQA, we can compute multiple query heads per KV head, right? So here's an example. So usually to do matrix multiply, the tensor core instruction can deal with on the order, the unit it deals with is like 64 by something, 128 or something, right? On the M dimension, on the query length dimension. So if you have a very short query length, 1 or 4, if you're doing speculative decoding, then you're sort of essentially wasting uh, most of the output of the tensor core, right? Like on this direction is the query length, on this direction is the KV, and if you only compute like 4 tokens or even 1 token, then the matrix multiply is pretty much wasted, right? But if you have multiple query heads for GQA, you can pack them together into um, uh, into one tile, and then you can use one MMA instruction to compute them. Um, but this is called GQA packing, and it's actually helped quite a lot compared to FlashAttention 2. Um, Especially for things like speculative decoding, where you have query length on the order of 4, and you might pack 16 query heads together. So this I'm showing the 10 low is better. So in many cases, GPA packing make a big difference. Right. And then finally, I'll talk about some optimization for multi-head latent attention, MLA. Um, so for MLA, this is this attention variant from DeepSeek, and during decode, what happens is that the head dimension becomes quite large. So normally we would have head dimension 128 or 256, but for MLA, the head dimension is like 500, right? And so if you use the standard way of splitting it, we don't have enough registers, so we have to split slightly differently, is that we can normally would split along the M dimension, the query length dimension, but now instead we're going to split along the uh, uh, the head dimension. So head dimension, instead of 512, we're going to assign it to 2 warp groups. So warp group 1 will do the matrix multiply for Q and K, um, and then they will pass the result they will use the result to compute their own P times V, but also pass that softmax probability for the second work group to do P and V, right? And so if you split it this way, you actually do have enough registers. And this works quite well. You actually get very high teraflops, very high compute utilization, even during decoding. Decoding just 1 token. So this is just a surprising thing. So here I'm showing DeepSeek Flash MLA and FlashAttention 3. The implementations are very, very similar. DeepSeek is version sort of built on some of the code from an older version of FlashAttention 3 anyway. So they perform very similarly, but you notice that you can get to like 600 teraflops per second, even when you're doing decoding. Because it has very high arithmetic intensity, since you can pack like 128 query heads into each, right. So I think this is pretty much going to be people are going to take this idea and redesign the architecture for this. We see that usually attention is memory bound during decode, and that's been true for a long time. But I think MLA is sort of the first variant where you can get to compute bound. if you deploy with large query heads, which they do when um, and so I think more and more of these architectures would be designed thinking about inference first, right? There's some stuff on Blackwell, but I think I'm gonna skip in the interest of time. Um, and then I will just conclude. FlashAttention is a fast and accurate attention optimizing for modern hardware. Some key ideas are asynchrony and low precision. And I will also talk about some advanced techniques like persistent kernels, longest processing time first scheduling, split KV, and GQA packing. Um, and the upshot is you can get faster training, you can get faster inference and better models with longer sequences. Um, so I'll stop here, and if there are more questions, I'm happy to answer them.
I would love to ask a question.
Yeah.
So if you have a lot, if you have a very large context size, I was thinking that you couldn't actually fit the queries and keys into memory, so you have to constantly like reload them, right? Because they might not even fit the cache if you have very large context windows. So is this actually a problem?
So how large are we talking?
Billions.
Billions, yeah, it definitely doesn't fit. So you would either have to do context parallel, which means you split it across um, multiple devices. Some people have done that. Um, or as you said, you constantly reload. I suspect constantly reload would be a little bit too slow. So I would say context thing on the order of uh, tens of millions or billions is probably an open question right now. Um, I don't think we don't have models that can deal with that, and two, on the system side, I don't think we have a good solution for how to do inference with that kind of context length.
Would it at that point become memory bound for sufficiently large context windows?
Whether it's memory bound or not actually depends on um, for GK packing, it depends on how many query heads per KV head. It doesn't actually depend on the KV length. Um, because when you think about the longer the KV, also, so more memory you need to load, but also more flops you have to do, right? Um, but so, so what matters is for each KV you load in, how many queries does it multiply with, right? So if it's only multiply with one query, then yes, the flops is so small that it's going to be memory bound. But if it's going to be multiplied with like 64 queries, 128 queries, then it can actually become compute bound. But yes, in general, people um, are not going to have that many query heads. Um, so it might be like 16 to 32. And so attention will generally be memory bound, right? And the longer the context, the longer the fraction of time you're doing attention. So as a whole, your end to end is going to be more memory bound. Yes.
Thank you. So does it make sense to like I'm just interested my research is in quantization. Does it make sense to design quantization kernels for very large context windows?
Um, I think so. I think even FP8, you can go much lower than FP8, right? I think FP4, some people might have done like 2 bits and so on. Um, I would say, yeah, that seems sensible, and that can probably be combined with other techniques like sparsity. You're going to drop some tokens or you're gonna have multiple layers users sharing the same KV cache and so on. I would say definitely, yeah, as we deploy these things in practice, we do worry a lot about the KV cache size. I would say that we also when we quantize, we also worry about whether when you're going to do dequantization, is it going to be fast on hardware for large batch. Um,
Maybe
so
want to do something more like hierarchical, like maybe you don't want to attend to every token. You want to make like to combine tokens somehow. Um,
right, yeah. So I think that is sensible, but that's going to be a little bit harder to do. Um, but maybe we'll figure that out in the next year or so, given so much demand.
I have maybe also one question. Do you think intuition for that we get so good in terms of flops close to matrix multiply is that we that you do so good job in scheduling that you yeah, I mean hide the effects of all the other operations by scheduling them in the way that I mean you essentially do almost just matrix multiply and schedule everything else
Right.
so
Yeah.
good.
So that's the intuition. Yeah. So the way you think about modern kernels, especially for compute bound kernels, is that you just want to keep the tensor cores as busy as possible. And for matrix multiply is, that's what they think about. They want to load in when you do A times B, you want to load in A and B. You want to pipeline the load so that the tensor cores are always busy and the sort of the next A and B tiles are always ready for the tensor core to compute. And similarly for attention, we want to pipeline the load, the K and the V for the next attention style, attention. But also there are a bunch of other things like prolog and epilogue and the softmax that you really want to hide or overlap with the tensor cores. So yeah, so that's the right intuition is that in some sense, all the flops, almost all the flops on a GPU and on TPUs and so on are in the tensor cores, right? So if so anytime the tensor core is idle, that means you're not reaching sort of the full flops, right? So one way to think about writing these kernels is how do I keep the tensor cores as busy as possible?
Yeah, thank you. And maybe one more follow or one more hardware related question is, do you know why, or I mean, why instruction for carrying out exponential is not further optimized, given that we, are so dependent on this operation and
Right. Yeah, that's a great question. So the reason is that, and I'm speculating here, is that um, the hardware is designed about 2 to 4 years before it's out, right? So when they design Hopper and Blackwell, which was probably 2 years or 3 years ago, they weren't thinking about attention as much. They weren't like really working out, how long each the matrix multiply is going to take and how long the exponential is going to take. Now the folks at NVIDIA, they've already announced that. So starting with the Blackwell 300, not the 200. They're gonna double the instruction throughput of the exponential, right? So they do understand this, but yeah, just designing it in hardware just takes a long time. So there's a latency there around 2 years, 3 years for something to be baked into hardware. And in general, I think why is Tensor Core so fast compared to everything else? There's this thing called a systolic array. I don't think tensor cores are exactly a systolic array, but I think TPUs have been explicit that they use systolic arrays, which allows you to do matrix multiplication very, very quickly because of a lot of data reuse, right? You think about matrix multiplication, the input in A and B, when you multiply and you get C, the ratio of flops to byte load is actually very high. Right. And you want to think about data movement is actually expensive. So that's why tensor cores and systolic arrays have so high throughput. But almost everything else has relatively low throughput because you have to pay a lot for data movement. You have to pay a lot in terms of chip area, die area, and power. So um, so I don't think there's an easy way to do exponential very, very fast. We're working on something, but on the hardware side, starting with the GB300, so they will double the throughput of the exponential.
Yeah, thank you.
Are you working on linear attention, like flash linear attention?
So Silent has been working on that. We do collaborate. I'm working on, that's still something that I'm interested in. So I think in maybe in 3 months or something, we'll have something. We'll put something out in that direction. All right. Really great to be here and talk to you guys about this stuff. Thanks for your attention.